老师 OK 了。
OK， 好。Okay, so very short is like we actually already finished the description of the algorithm. Okay, so we just use the stable sort from the least significant digit to the most significant digit. Okay, just sort these numbers one digit at a time. Okay, so that's it. 就从最右边那一位那一位，就是一个受到最左边那一位，就这样。So this is an example. You can see that in this case we have some 3-digit numbers. So we first sort from the least significant digit, so which is the leftmost digit. So you can see that, okay, we try to rearrange these numbers according to this leftmost digit, okay, but with a stable sort, okay. The result is like this, and then, okay, from here you can see, for example, we have 2, 7, right? 2, 7. So 4, 5, 7 appear in front of 6, 5, 7. 4, 5, 7, 6, 5, 7. And we have 2 9s too. 3, 2, 9 and 8, 3, 9. So 3, 2, 9 appear in front of 8, 3, 9. So you can see this is not like random consequence. This is because we intentionally choose a stable sorting algorithm here. Okay, so the stable sorting algorithm, there are many stable sorting algorithms that fit the description here, but the most appropriate sorting algorithm for this purpose, obviously, is the counting sort. Because first, the counting sort runs very fast, right? I mean, we just mentioned it's linear time. Second, okay, because we sort each digit, okay, if you use the counting sort, then because basically we only care about one digit, right? So the range of k is limited from 0 to 9. So it is like regardless how big how many numbers you want to sort, because we only deal with one digit at a time. So the k in the counting sort, is limited to 10. So it's very, very convenient. Okay, I mean, assuming we are using the decimal numbers. Okay, so anyway, okay, from left column, we go to the second column here, and then we deal with the center digit again by using the stable sort. Okay, and this will result in the third column here, and then here, okay, we deal with the most significant digit, leftmost digit. Okay, again, use the stable sort. Then the resulting list of numbers will appear on the right-hand side, and these numbers will be guaranteed. Will be guaranteed to be sorted. Okay, so this is what we call random sort. Okay. First, obviously, we need to make sure, because this is not like a little bit different from the previous sorting algorithm. I mean, a little bit complicated. Okay, I mean how do we make sure the concept is correct, right? So we need to prove that. Okay, I mean it's not like for example, quick sort or like even the counting sort, I mean, looks like you know, it's almost like you know, we can almost sure it is correct without very like you know, I mean, rigorous proof. But here, okay, we can actually provide a very quick, like a quick proof for the regular sort. Okay, basically it's like by using the induction. Okay, so assume the numbers are already sorted by their lowest order, low order t minus 1 digit. T minus 1 digit. Now we sort on the digit I. Okay, we sort on digit I. Maybe you will argue, how about like the basic case? Base case. The base case, basically, we just solve the most significant, the least significant digit, right? So obviously, like after you finish the sorting, the least significant digit appear to be sorted. So not much to argue here for the base case. So here is that we assume that this is the top one is induction hypothesis. Then we want to, I mean, when we sort, after we finish sorting on the digit I, digit t, okay, can we say like you know, from the least significant digit to digit t, these numbers are already sorted? Okay, basically, okay, there are two cases to discuss. First, two numbers that differ in digit t. Okay, if they are different in digit t, because it is by far the most significant digit. Okay, so if they are different and we sort on this number, on this digit, obviously it will give us the correct sorting result. 就是说，你看嘛，就是说，这个到目前为止这是最大的一个位数。如果说前面位数，如果这个位数是不一样的，你一定是按照这个位数排，对不对？对，你不管前面，就是说你前面假设99，你这个是00，不重要。你百位数假设是2，另外那个00是3，那就是300已经到了299，这个没有什么，很容易就可以知道了，对不对 ？Okay, it's a you know easy to understand. When two numbers are different, then you should so you should arrange this number according to their digit t. Okay. How about if they are the same? The two numbers are the same in digit t. If they are the same, then the previous digits are already sorted, right? So the stable sort guarantees that we are not going to change the order of these numbers, right? Because of the stable sort property. So we are still going to result in correct order. So regardless, which case that happens, we have the correct result. So yeah, so that's it. And then, okay, is the analysis. Okay, how about the time complexity? Okay. So as I said, okay, usually, I'm not saying that it's always the case. I'm not saying it has to be the case. You could use any stable sort, okay, for a given digit, okay. You could use the merge sort, you could use the bubble sort, whatever sorting algorithm you prefer, as long as it's a stable sort. It works with the radic sort. But if you consider, if you care about the complexity, obviously, counting sort is the best. In terms of like the time complexity it has the lowest order because it's a linear. Okay, so assuming the auxiliary sorting, the algorithm we use to sort each digit is counting sort. Okay, Then, okay, when you want to solve n computer words of b bits each, okay. So depending on your system, okay, each system may have different bits for one word. I think you probably have learned that from your computer architecture class, right? 你在你的计算机结构、计算机组织里面应该学过，说不一样的那个计算机那个硬体的话，它的那个一个 word 的定义有可能是不一样的，有可能16 bit， 有可能32 bit， 对不对 ？Depending on your hardware， the word may be 16 bit, it may be 32 bit. Okay. But anyway, okay, assuming it's a b bit, okay, each word is b bit. So each word can be viewed as having, okay, b divided by r base 2 digit. Okay, so if you have 32-bit word, okay, and r equal to 8, okay, so r basically is like each round, how many digits we want to use to in our stable sort. I mean, in the previous example, in this example, I mean, we use 1 digit, okay, because it's decimal. 这是十进位，所以我们每一次的每一个iteration， 我们只处理一个 digit. But it is not because when we discuss high complexity, okay, because we are dealing with binary numbers, 就是那你一个 digit 就只有两个零或一嘛，那你不需要只处理一个 digit， 你可以处理好几个，对不对？就是 that's the basic idea. So if each round, each iteration, we deal with 8 bits. Okay, 就是每一次 stable sort 我们处理八个 bits. Okay, but 8 bits is really not a lot of numbers. 8 bits is like how many? 256, right? 256. Okay, so k is bounded by 256. So still, it is considered a small, small number. So, okay, so if r is 8, so b divided by r, because our word is 32 bit, so b divided by r is 4. So we need 4 passes of counting sort on, 2 to the power 8 digits. Okay, if r is 16, so b divided by r is 2. So we need 2 passes of counting sort on base 2 to the power 16 digits. Okay. So depending on how big or how many digits we want to deal with for one pass. Okay, I mean we may end up with more passes, but each pass obviously time complexity will increase. Right? So how many passes should we make to optimize the time complexity? So if we try to write it more formal, okay, the counting sort takes theta n plus k time to solve n numbers in the range from 0 to k minus 1. So if each b bit word is broken into r bit pieces, then each pass of counting sort takes theta n plus 2 to the power r time, because k will range from 0 to 2 to the power r minus 1. So k, the size of k is 2 to the power r. So since they are b divided by r passes, so the time complexity t of n comma B because here the B is maybe become variable considered in the time complexity. So it's going to be theta B divided by R n plus 2 to the power of R. So you need to choose R to minimize this T of NB. So increasing R means fewer passes, but if R is larger than log, then the time grows exponential because R appear in the exponential part of your time complexity. So you need to choose R wisely. So how to choose R? We could one way we could do it is that we could differentiate this formula. Okay, we can differentiate this formula and set it to be 0. Okay, to come up with a right choice of R. But we can just observe. We don't want 2 to the power of R to be too big. Then if 2 to the power of R is too big, then there's no harm. Okay, because of this observation, there's no harm asymptotically in choosing R as large as possible. Okay, subject to this constraint. So the easy choice is we choose R to be log n. So let's see how the formula becomes when we choose R to be log n. Because when we choose R to be log n, the parentheses, inside the parentheses, it becomes n plus 2 to the power log n. So it's the parentheses become n. And then, because R appear outside the parentheses, appear in the denominator. So it's log n is Bn divided by log n. Okay. And for numbers in the range from 0 to the nd divided by 1, minus 1, nd minus 1. Okay. Where this nd means that the word, okay, the size of the word. Okay. So we have B equal to D log n. Okay. This B actually is the D log n. So very short. You plug in B to be D log n. So log n cancel each other. So the radical runs in theta D times n times. So it is linear as well. So it is very, very efficient sorting algorithm. Okay. And by the way, this is also one of the sorting algorithms I request you to implement in the first lab. Okay, the first lab. So in conclusion, okay, random sort is best for large inputs. Okay. And it is also very simple to implement. Okay, it is simple to maintain, which is nice. But, okay, when the number is not that big, okay, for example, like 32-bit numbers, so at most 3 passes, when sorting like 2,000 numbers. So merge sort and quick sort, okay, because the best case is divide even into a kind of binary tree, right? So it requires log 2,000, so roughly 11 passes. So when the input is large, ready sort is good. Okay. So but unlike quick sort, ready sort display little locality or reference. So, you know, a well-tuned quick sort, you know, can work better for modern processes. So in our quick sort can be tuned for hardware like acceleration. Okay, easier than the rally sort. So even rally sort, you know, appear to be faster for large numbers, but in practice, okay, the quick sort is still it still has the advantage in terms of hardware acceleration. Okay. So anyway, just want you to give you an idea. Okay. I mean, it's not like the comparison-based sorting algorithm are always, you know, inferior than the linear time sorting algorithm. It depends. It depends. But you know, that's it for all these sorting algorithms. Okay. The following are some like I mean, histories for the punch card technology, I mean, which is like obviously like the ancestor of the computer, the modern computer. But I will skip this one because after all, you know, this class is not like a history class. But you are more than welcome to check out this content by yourself. Okay. This is the Herman Horowitz. I mean, this guy, like, he invented like a radio sort. Okay, so that's it for all the sorting algorithm. But the next one, okay, although it is not considered a sorting algorithm, it is also, what should I say, like, kind of like similar to sorting algorithm. At least like it has some idea like we can borrow from the sorting algorithm. Okay, that is like order statistics. Okay, what is order statistics? Okay, order statistics means like if you, I mean, given a list of unsorted numbers, you want to find the rank I from these numbers. Okay. What is rank I? Rank I means like you know, the i's largest number. Okay. In this unsorted list. Okay. So the i's smallest. Actually should be i's largest, right? How do we say that? Okay, anyway, okay, of n elements. So the element is the rank I. So when I is 1, we want to find the minimum. Okay, I is 1, we want to find the minimum. When I is n, assuming we have n numbers, then we want to find the maximum. So if I is like you know, roughly half of n, that means we want to find the median from these numbers. Okay, so that is what we call order statistics. Okay, so a naive algorithm to do this job is that we can just sort numbers and you know, whatever index I, we just you know reference the index I. Okay, use the index I to find that number, and that's it. That's it. Okay. So worst case, running time. Okay, for this approach, for this naive approach, is theta log n plus like we need a constant time to find the ith element from the sorted list. So the complexity obviously theta log n. So what sorting algorithm should we use? We could use merge sort, we can use deep sort, but not quick sort. why don't we use quicksort? Because quicksort, the worst case, time complexity is n squared, right? We know that. The expected time complexity for quicksort is n log n, but not the worst case time complexity. Here we are talking about worst case time complexity. Okay, so the worst case running time, I mean, if you want n log n, it will be merge sort or deep sort. Okay, so this naive approach obviously works. Okay, it works, but if we want something better than that, can we do something better than that? The answer is yes. Okay, we could. I mean, I probably need to explain a bit more. Okay, the first approach is a randomized algorithm. Okay, it's a divide and conquer algorithm. Basically, it is the algorithm that stems from quicksort. Okay, because you guys already understand quicksort, right? So in the quicksort, we know that if you pick a pivot, after the one pass, one iteration, you find the location of that pivot, right? Okay, so basically, okay, I mean, if you want to find the rank I, so if at the end that pivot is at the location R, so depending on the relationship between the R and the I, right? If R equal to I, you already found that number, right? Which is a pivot. If R is greater than I, that means you need to find the I's smallest element from the first half, right? If I is greater than R, that means you need to find I minus R, smallest element from the second half, right? Something like that, right? So this is obviously a recursive approach, right? Okay. So an example is like this. Say we want to find the seventh smallest element. Okay, and the pivot is we just use the first element as pivot. So after the first pass, okay, I'm not going to the iterate how we do the iteration again, But anyway, at the end of the first iteration, 6 appear here, which is index 4, right? Index 4. So index 4 is smaller than I, right? So you need to find 7 minus 4, okay, which is 3. So the third smallest element from the second half, right? So that's it. You need to do this recursively, but that's the basic idea, right? Okay, very, very simple, right? So, so what is the complexity here? Okay, so again, something similar to what we discussed for quicksort. Okay, if we are lucky, say every time we are able to divide these numbers, if we select pivot luckily, okay, every time we select pivot, it is able to break the numbers into a certain ratio, okay, with a guarantee, okay. Then, for example, 1 to 9. Then what happens the time complexity becomes something like this. So it's going to be linear. If it's unlucky, then what happens that every time we can only get rid of one number. Okay? So it becomes arithmetic series. So it's a theta n squared. Okay? So if it's theta n squared, it's worse than sorting. is worse than that naive approach, right? Because naive approach is n log n, right? So here we need to check careful. Okay, the analysis actually goes through. I mean, very similarly to what we did for quicksort. Okay, so again, we assume there's a random indicator random variable. Xk means like it is one if partition generate a k to n minus k minus 1 split, 0 elements. Okay, so that's this indicator random variable, the definition of indicator random variable. Okay, so k can range from 0 to n minus 1. Okay, then your Tn, the time comparison can be represented by one of these, right? One of these. Now each time, each one will give us theta, and basically it's like one iteration, split in the pixel. Okay, so basically, okay, if you try to represent, because only one of them will happen, right? Only one of them will happen. So you could use like an xk to write it like this. Okay, so this part, the analysis is very, very similar to what we did for the quick sort. Very similar. So then, here we have this, and then, we can put it into this expectation. Give expectation on both sides, and the expectation on the right side can get into the summation because the linearity of the expectation. And then, okay, we can, again, put the expectation into like each term. Okay. So because the xk is independent from other random choices, and then eventually becomes something like this. First, like the right hand side, the second term obviously is just theta. Okay, and this is similar to what we did for the quick sort. And the first term, okay, actually like it will be like this part is similar to what we did for the quick sort. Okay, so half of the index are the same, which is get like something this one. And then we have like a fact, this one. Again, this is an exercise. We'll just use it, okay? But in the exam, in the homework, I will ask you to do that, okay? So we use this fact, okay, and then we are able to prove this recurrence relation. Okay, it's going to be, expectation of the Pn is going to be smaller or equal to Cn. Okay, why? Because like we can use this fact in here. So this is like we use like inductive hypothesis. Because like this k in here is lower than n, so we can use ck to replace that. And from here we can use this fact, okay, to become like this. And then this one, after we rearrange that, we have Cn outside minus Cn divided by 4 minus theta, and so as long as we pick our C large enough, okay, to bound this linear term, okay, then we have our case. Okay, so basically here, all we are talking about is that we are able to use induction to prove that, okay, the expected time complexity for this randomized algorithm is linear. It's linear, which is very nice, right? Because remember, if we use the naive approach, the worst case is n log n. Okay, use this randomized approach, the worst case is n squared. It's worse than the naive approach, but the average or expected complexity is actually linear. Okay, in practice, this is actually pretty nice. It works pretty nice. Okay, it works pretty nice. Okay. So summary. Okay. I mean, you know, the randomized approach works fast. Okay, linear expectation time, and it's an excellent algorithm in practice. But the worst case is still like n squared. So is there an algorithm that runs in linear time in the worst case? The answer is yes. There is an algorithm proposed by Freud and Pratt and the Rivers and the Target in 1973. Okay, that is able to run in worst case like linear time. Okay, the idea is to generate a good pivot recursively. How do we do that? We will talk about this algorithm, but today because we are running out of time. So next week we are going to finish up this part, okay? And hopefully continue our discussion, which will be, I hope, before the midterm we'll be able to finish the sorting algorithm part. Obviously, we are about to finish everything, and we'll also cover the hashing. Okay, because sorting and hashing are two fundamental but very commonly used algorithm everywhere. So we are going to cover these two parts and then move on to the other parts. Okay, after the midterm. Okay, and let me remind you again, the midterm will be conducted in the 8th week, which will be the middle of August. Okay, and what else? There will be a programming exam. They will take place not exactly a week after the midterm, the following Tuesday after the midterm. Okay. So any questions so far? If no questions, that's it for today. Okay. So I will see you next week. And remember, the homework 2 has been uploaded in class. Okay. Please check it out. Okay. You have more time to work on this homework because this homework is long. Okay. There will be more questions there. Okay. Okay. Thank you.